Okay, hello everyone. Today I'm going to tell you about binomial theorem. Well, Newton first came up with it. So, uh, the binomial theorem basically says that if you got a binomial x plus y raised to the nth power, then this, when expanded, can be written as n choose 0 times x to the n y to the 0 plus n choose 1 x to the n minus 1 y to the 1 plus n choose 2 x to the n minus 2 y to the 2 plus n choose 3 times x to the n minus 3 and y choose 3 all the way till n choose n. X to the n minus n is 0 and y to the n. Okay, so how do we prove this thing? Well, first of all, you need to consider this in a different format. Okay, so you got x plus y raised to the nth power. That's going to be x plus y times x plus y times x plus y, and yeah, n of them. Okay, these are n x plus y's. Now I want you to find out what is going to be the coefficient of this term, x to the n minus k y to the k. Well, from the previous expansion we know that the coefficient is going to be n choose k, but how do we get that using combinatorics? So if you really think about it, we need to find all the ways in which we can generate this thing, x to the k and y to the n minus k, from this expansion, and we can only do that by multiplying k x's and n minus k y's. Okay, so consider every single term without recombining. What do I mean without recombining? So suppose you got x plus y into x plus y, that is going to be x squared plus 2xy plus y squared, but that is after recombining. If we didn't recombine it, it would be x squared plus xy plus y squared. So consider every term like this, which is not recombined yet with other terms of its liking. Okay, if we consider these terms, uh, then I want you to understand that if we want to generate x squared, okay, the only way we can do that is by multiplying two x's together, and in these two brackets, the number of ways in which from which okay number of ways in which we can multiply two x's together is just 1, and that's why the coefficient of this x squared is 1. But the number of ways in which we can multiply an x and an y, there are two ways in which we can do that, which is first by multiplying this x by this y, and secondly by multiplying this y by this x, and that's why you have two of these over here. And then for y square, that's by this times that, only one way in which we can do that from these two brackets. Similarly, if we got another x plus y over there, the number of ways in which we can make an x squared y is, first you can have 1x from here, 1x from here, and 1y from here. That's one way. Then you can have one y from here and two x's from these two brackets, so that's another way. And you got a third way, where you have these two x's and the last y from this. Okay, so these many of x squared y's are going to be there, because these are the number of ways in which an x squared y can be generated. Okay, and every way is going to generate a unique x squared y, just like we saw over here. Every way, which is x times y and y times x, both are going to generate their unique uncombined term. Okay, and then the number of terms which are in liking with this thing, I mean how many of these things are going to be generated through these unique ways, those are going to be the number of ways in which we can multiply x and y, right? And those are namely two over here. Okay, so basically we need to find that in how many ways can we get k x's together and n minus k y's together from this big multiplication. Okay, so suppose you got k x's together from k brackets, automatically the other n minus k brackets, those are going to give you these y's, so you don't have to worry about that. So basically we only need to find k x's from these n brackets, and the number of ways in which we can find these x's is n choose k. Okay, some of you might know this is the binomial coefficient, this is the choose function, this is basically n factorial upon n minus k factorial into k factorial. All right, these are the number of ways in which we can choose k things from n things. Okay, so that tells me in how many ways can these be generated, and exactly how many of these are going to be in the not yet recombined expansion. So yes, that means that this is going to be, I mean, this is going to be the coefficient of this term. So that's how this thing works. That is a very nice proof of it. There are other proofs as well. There are some proofs which use mathematical induction. Those are much easier to understand because they are more algebraic. But this is the actual proof, and actually how Newton came with it. It involves combinatorics. So that's how the binomial theorem works. Suppose you got something like 2 plus 3 to the fifth power. You could either do it like this. You could do it 5 plus 5 to the fifth power. That is going to be, instead of doing this, you just use algebraic expressions. That will be much better. So suppose you got x plus y to the fifth power. This thing, using that theorem, the binomial theorem, this thing can be written as n choose, okay, 5 choose 0. So 5 choose 0 is 1 times x to the 0th power, y to the 5th power, plus 5 choose 1 is 5 times x to the first power, y to the 4th power, plus 5 choose 2 is 5 times 4 upon 2 into 1, that is 10, x to the second power and y to the third power. Then 5 choose 3 is the same as 5 choose 2, which is also 10. You got x to the third power, y to the second power. And similarly, it's going to be 5 choose 4, which is the same as 5 choose 1, which is 5. And you got x to the fourth power, y to the first power, and then 1 x to the fifth power, y to the 0th power. This is confirmed by the Pascal's triangle, the famous Pascal's triangle: 1 1 1 2 1 1 3 3 1 1 4 6 4 1 1 5 10 10 5 1. So this always works. It works all of the time. It's very beautiful, and it is involved in a lot of proofs of which Newton gave. Okay, it is also involved in, I think, the proof of y derivative of x to the n is n times x to the n minus 1. Yes, so that is the binomial theorem. Very powerful and very nice to have in your mind. Okay, thank you for watching. I'll see you in the next video.